Okay, here's a really common experiment in questions. It's where we take two things, one hot, one cold, and they change to an intermediate temperature. This is known as method of mixtures, and sometimes it is used to find the specific heat capacity of something. So for example, I'm going to take this block of iron and try and work out what its specific heat capacity is, but other times it might be to try and find out what happens to the temperature. So what we're going to do is we're going to put this into liquid, a bit like adding cold water into a hot bath. So I'm going to take my copper calorimeter, okay, it's a known mass and it's a pure material, so I know its properties, and I'm going to put that into there and heat it up. Now, to make it work best, I'm going to put some liquid into that. So let's just get some data. This is all the data I'm going to need to copy, so need to have. So first things first, the mass of my iron is 0.251 kilograms. The calorimeter itself, not the insulation, not the bit in the middle, we're going to assume that's going to really limit the heat coming out. As it says on the outside, should be 119 grams, that's 0.119 kilograms. The specific heat capacity of the calorimeter is 385 joules for every kilogram, so it's not going to take that much for 1 degree rise on that. So I'm going to put that back into there. I'll tell you what, let's measure the water in a separate way. I'm going to put some water in as well, because we know that mass already and we know the density of water is 1,000. We can do this in a nice easy way. So I'm going to take that up to about, there we go, a random 187. So if you take off the 119, that's going to be 68. So 0.068 kilograms. Now I'm not putting much in. If you look, there's very little in there, and the reason is the water's going to it's going to come up when I put the iron in. But more importantly, the more water, the more energy I need to heat it. So for the same energy, the more water, the less it will heat up, and I want a big temperature range. So I'm going to put it into there. I'm going to take this, I'm going to stick it into some freshly boiled water. The temperatures are going to be quite subtle. So the temperature is going to be quite subtle, so I'm going to use a data logger to actually get that to working best. A good mass of water, so lots of energy. It's not going to cool down much, it's going to give me a nice big range. What I'm going to do is I'll take my temperature probe and stick it in that water at the beginning. I'm going to take a temperature probe and stick it in the water there at the beginning, and I'm going to take those temperatures and I'm also going to see how much they run. Okay, so how much they're going to change. So at the moment, we have, pause. So we have one of these, if I just bring my picture back in, my cold water before I put anything into it is at 21.8 degrees, and my hot water where the metal is, and the metal is of course a good conductor, so we're going to assume the heat goes through that fairly quickly. It's been sat in there 30 seconds, so that should be good. That's going to be 84.1 degrees. Okay. Now, nice quick experiment, so we don't really need to worry about heat loss in this experiment. I'm going to take some tongs, because this is fairly warm, I don't want to stick my fingers in it. I'm going to take that out, try and shake off any spare water from it, and plop it into there. Okay, and I'm going to knock it over so it's well enclosed. Okay, and that temperature is shooting up, and we can lock that down so you can see where it's going to. 29, etc. The blue one is the cooling hot water. Now I've taken the metal out, it's making a bit of a difference. But the final temperature seems to be in the region of 33. It's probably going to level off high 33s. Okay, we want the peak before it starts. So we jumped a bit in the recording there, but our water finally ended up at 35.1 degrees C. So the idea is that we're trying to work out how much energy has gone from here, okay, in terms of our hot metal, leaving that to make it cool, and therefore taking the heat and putting it into this, so the same amount of energy goes in because we're assuming no heat loss, and therefore that's going to warm up 35 to 35.1. Now you'll see straight away that actually that's not a big rise. Much bigger change is from this down to this. That's kind of almost 50 degrees. That one's only about 14 degrees, which shows that the specific heat capacity of all of this is much more than the specific heat capacity of that. But the idea is, with all of these, you know that the energy, the amount of energy that goes in or out, is mass times specific heat capacity times temperature change. So in this case we don't know what that is, but we do know that, and we can get that from the amount of energy that went into this to therefore make it heat up to 35.1 degrees. Okay, so really common, very much like putting cold water into a bath to cool it down, just guessing how much water you're going to put in, or nuclear power station, coal power station, gas thermodynamic power stations, the substance that takes the heat away from the reactor. Yeah, so all our values are there, all our masses, the cooling iron, the heating water and heating heat capacitor, how massive each of those are, the water and the calorimeter to go in, and specific heat capacity is in joules per kilogram per Kelvin, but a Kelvin change is also the same as a degrees centigrade change, degrees Celsius change. Okay, so you can use those numbers to just stick them in and say, in this case, we're trying to get to this value here. Okay, and let's see what value you come up with, see if it's close to the accurate one.